This is the lecturette for the first half of Chapter 11, talking about the properties of liquids, sections 11.1 through 11.3. And we're going to review first the phases of matter and phase changes on the molecular scale. And the bulk of what we'll be talking about are the properties of liquids. And so in this chapter, we talk about the properties of liquids that we can actually see experimentally. That's what we're doing here now. And then after that, we'll talk about how we envision those being controlled by molecular structure. And so the properties we'll be looking at are enthalpy of vaporization, boiling point. Enthalpy of vaporization is how much energy it takes to vaporize a liquid, either a mole of it or a gram of it. Boiling point, you know what that is. And then we'll relate vapor pressure, boiling point, and enthalpy of vaporization. Vapor pressure is essentially how much pressure a gas that arises from vaporization of a liquid causes. And then we'll look at some other important properties of liquids: surface tension and viscosity and capillary action. Okay, so we're first going to talk about phases of matter on the bulk scale. And as you know, solids and liquids tend to have similar densities, whereas both of those are much, much greater than gases. So gases have very low densities, and solids and liquids have relatively high densities that are close to each other. Gases have generally weak intermolecular forces between particles, and molecular forces are the forces between molecules or atoms. They're very, very weak or almost nothing. They can be compressed, meaning you can push on them and they take up less volume, and they take the shape of a container and they flow well. Liquids also flow well. They take the shape of the container, but they fall down to the bottom, unlike gases which fill up a container. They can't be compressed well, and they generally have intermediate size strengths between molecules holding them together. And solids have strong strengths of molecules holding them together, almost no ability to compress them, and as you know, they don't flow, they hold their shape, they are what we call rigid. And so the reason for this on the molecular scale is seen in the simulation we've used, that when you have a solid, the molecules or the atoms can jiggle around a little bit, but they can't move past each other. And when you heat them up, what happens is eventually they get to a place where they're still pretty much attracted to each other, but they can start moving past each other. And this is essentially a liquid here. That is, it can flow because one molecule can move past another molecule. Now and then one escapes into the gas phase, but for the most part, this is a liquid. And then when you heat it up even higher, you reach a temperature at which the kinetic energy of the molecules causes them to completely not be able to stay near each other, or not very much, and then you end up with something in a gaseous state, which is what we have here, where the molecules are basically acting as independent entities, and they bash against each other and stuff. So what this chapter is really about is the properties of liquids, in that, for example, neon will go from the solid state to the liquid state at a relatively low temperature, around 30 Kelvin. It'll do that, and not much higher than that it goes into the gas phase. If you take oxygen molecules, on the other hand, at that same temperature, 69 degrees, they're acting pretty much as a solid, just barely beginning to melt, and they melt at a much higher temperature, and then boil at yet even a much higher temperature. So what is it that causes one molecule or one atom to have to be at such a much higher temperature than another one to cause it to either melt or to vaporize or to boil? And as you know, water, of course, at 153 Kelvin would be just a liquid or a solid. Whoa, why is that so high? Don't be so low. Get back to the solid state, you. So at 157 Kelvin, water is not. Water molecules are holding right near each other because they don't have nearly enough energy to escape each other, because their forces between the water molecules are much stronger. And so that's what we're going to be talking about. Okay. So in all cases, all phases of matter, the molecules are in motion. For liquids and gases, the molecules can move freely, meaning they can move past one another. That's why they can flow. That's why they are fluid. Fluid. It's a nice word to say, fluid. Liquids and solids have molecules in close proximity. They're staying near each other. But only solids have molecules that can't move past one another. That is, that rigid. Okay. Phase changes are when one phase changes to another phase, obviously. Fusion is the same thing as melting, and that's when a solid becomes a liquid, and that requires energy. Energy is absorbed for that to happen. Vaporization is when a liquid goes to make a gas. That is essentially boiling, and that also requires energy. And sublimation is the direct transfer of atoms or molecules from the solid state to the gas phase, and that also requires energy. So whenever you go from solid to liquid to gas, that requires energy. The reverse of these processes are freezing, which is solid to liquid. You know that. When you freeze something, energy is actually released. You think of freezing as cold, but for the thing that is actually freezing, it releases energy when it freezes. Condensation is when a gas turns into a liquid. Energy is released for that too. And deposition is when a gas changes to a solid. It's the opposite of sublimation. And that also releases energy. So what happens is, if we think about it on the molecular scale, what happens is if you take a glass of cold liquid in a glass on a humid day, a warm, humid day, what happens is, you know that after a little while you get the outside of the glass gets wet. Is that from the water leaking through the glass? Well, of course not. Of course it's not that. What's happening is water molecules in the gas phase are condensing on the cold surface of my heart. It's a good phrase. Use it for something. And when they condense, they end up having stronger attractions to one another because they're at lower temperatures, and it makes a liquid. So that's the liquid. This is the gas. And so that's a phase change. That's condensation. It happens because here, when it's warm, the molecules have enough energy to break the intermolecular forces between them. Here, when it's cold, the molecules don't have enough energy to break those forces, and therefore they stick together. So phase changes on the molecular scale require energy. That's plus energy. That's minus energy. This is plus energy. That's minus energy. And to go from solid to liquid, solid to gas is plus energy and minus energy. Okay. This goes back to something that's really important, and that is breaking bonds, or any interaction. Breaking bonds requires energy. Some biological systems are described as actually releasing energy when bonds break, but that's not true. It's more complicated than that, and breaking bonds always requires energy. Forming bonds always releases energy. Okay, so one of the important things is that different liquids have different temperatures. So if you take an alcoholic beverage, I believe this is brandy, or it might be whiskey. But I'm going to say it's not whiskey because I don't know how to spell whiskey. I don't know if it has an H in it or not. So what happens is you have brandy, and it has water, and it has ethanol, which we summarize in the trade as ETOH. But it's really CH3, CH2OH. And what happens is, if it's at all warm, you get what are called legs. It's a phrase I don't particularly like, but that's what they call it, legs, which is essentially what happens is the ethanol evaporates from the water, and when it gets up here, it hits the cool glass and recondenses. And so these little drippy things are alcohol that's coming up, hitting the glass and flowing down. If you look at things that have less alcohol, you don't see those because there's not as much alcohol to do it. So what that means, the thing that we're interested in, is that the ethanol has weaker intermolecular forces than does the water, and it's easier to evaporate it. And the ethanol has greater, what we call vapor pressure, meaning that it changes into the gaseous state better. Another way you would say this to just in common language is that the ethanol is more volatile. Ethanol is more volatile, so it changes into the gaseous state more, changes into gas. When it gets up here, it returns to the cool glass and becomes a liquid again. Okay, so ethanol has a higher vapor pressure because there's weaker intermolecular forces. Okay, so now we're going to start talking about the properties of liquids in detail. And the ones we're going to talk about are enthalpy of vaporization, which is written delta H sub VAP, and this is the one that most directly relates to intermolecular forces. It's the energy it requires to separate molecules of a liquid and make it a gas. So it's a direct measure of the strength of the interactions between molecules in a liquid state. Vapor pressure is a function also of intermolecular force strength, and that is that it's the vapor that comes from a liquid evaporating. So if you have a flask and it's stoppered and you have a liquid in the bottom, if the molecules of liquid go up into the gas phase, that gas there has a pressure. And that pressure comes from this liquid turning into a gas. And so when a liquid turns into a gas, that's called a vapor. And the pressure from that vapor is the vapor pressure. Boiling point is the temperature at which the vapor pressure reaches the external atmospheric pressure. And we'll talk about that later on. Surface tension is the tendency of a liquid to resist change. That is, to keep its surface at a minimum surface area. And viscosity is the resistance of flowing. It's how thick a liquid is. How thick. All right, so let's talk about enthalpy of vaporization first. It's conceptually very simple. You take a mole of a liquid, you heat it up, you add energy, plus energy, and you make a mole of a gas. How much energy does it take to do that? Take a mole of a liquid and change it into a gas. That is the enthalpy of vaporization. And for water, 1 mole takes 40.7 kilojoules. So therefore we say the enthalpy of vaporization for water is 40.7 kilojoules. It's always positive. It always takes energy to vaporize a liquid. And it's therefore endothermic. And the bigger the number, the more strongly those molecules are held together. Okay, if you look at some examples, you get ranges of really very, very low enthalpies of vaporization. Helium, I think, has probably the lowest of anything known, ranging up to fairly high. Water has one of the highest enthalpies of vaporization for common liquids. And the rule is the stronger the IMFs, the stronger the forces between the molecules, the larger the enthalpy of vaporization. And so the way we use this is we don't know the force of the intermolecular force strength and then figure out which enthalpy of vaporization would be bigger or smaller. In fact, we measure enthalpy of vaporization in the laboratory and then from that infer things about the relative IMF strengths of molecules we're interested in. So it's experimentally driven. On a molecular scale, where vapor pressure comes from, what happens is if you have a closed container, if you have no molecules of the gas of the particular compound or liquid you're thinking about, what happens is, the first thing that happens is some of those molecules will escape into the gas phase. When they do, that makes some pressure. Over time, what happens is some of these gas molecules will hit the surface of the liquid and go back into the liquid phase. And so at first, the liquid changes into a gas. And now over time, the gas also changes back into a liquid. And when the rates are the same, that is, in a closed container eventually, and actually happens pretty fast, what happens is the rate at which the liquid goes to make the gas and at which the gas goes back to make the liquid, when those are equal to each other, then you have the equilibrium of vapor pressure. And this is our first example of something that's really important in a lot of chemistry, and that's called dynamic equilibrium. The dynamic equilibrium means that if you look at the rate of evaporation and condensation, the rate of evaporation is happening the same. As you get more and more molecules in the gas phase, it's more likely for them to condense. So eventually those become equal to each other. And so at the point of dynamic equilibrium, there's no change in essentially number of molecules in the gas phase. So what you see is if you're actually measuring this, you see it stops changing. But it doesn't mean it stopped happening, because what's happening is even though you have the same number of molecules in the gas phase, they're not the same molecules in the gas phase, because some are always going out, and so is always going in. And let's look at this in our little simulation again. So let's go back to neon. Let's go to a liquid. And so if we heat up a liquid, what happens is some of the molecules will escape into the gas phase. But this molecule right here, look, it hit again, it went back into the liquid. That molecule there is in the gas, it's back into the liquid. This molecule here was in the liquid, and now it's a gas again. You can watch this all day long, but you're not gonna, because you got stuff to do. So what happens is some molecules are in the gas phase, some are going back in the liquid phase, but you have roughly the same number of molecules on average over time in the gas phase. And that is dynamic equilibrium. All right, so let's look at some vapor pressure trends, and we're going to do this using a simulation. And what we have is we have a simulation where we can choose two different liquids. Let's choose water. We like water. And we'll choose methanol. And what we do is we can change the temperature, and when we change the temperature, it'll calculate the enthalpy of vapor. It'll calculate the vapor pressure for us. So we have some liquid down here, some liquid down here. We have a pressure meter. And so at 6 degrees Celsius, it's probably like 40, let's go to 8 degrees Celsius. 7 degrees Celsius, so that's about 40 degrees Fahrenheit. The vapor pressure of water is 9.7 millimeters of mercury. It's really low. It's like around 1% of an atmosphere. But the vapor pressure of methanol is about 6 or 7 times greater. And as we increase the temperature more and more, they both go up. So there's two things that are important. So as we increase the temperature, the vapor pressure of the water goes up, the vapor pressure of the methanol goes up, but at all times, in this particular case, the methanol is always greater than the water is. So there's two trends we see. Two kinds of points to make. One is as temperature increases, vapor pressure increases. And different liquids have different vapor pressures. And so let's go back to our slide. If you look at the vapor pressure of different liquids at different temperatures, in all cases, as temperature increases, get back there. And in all cases, as temperature increases, vapor pressure increases, always. The other thing that's important is molecules with strong intermolecular forces have low vapor pressure. And the reason for that is the molecules are held in the liquid state. And so that's what happens. Molecules are held in liquid state. If the intermolecular forces are strong, not many molecules can get into the gas phase, therefore low vapor pressure. So you can look at, say, a particular temperature and rank different liquids for intermolecular force strength. So of these 4 liquids at, say, 75 degrees, diethyl ether has the weakest intermolecular force strength. You just know that experimentally because it has the highest vapor pressure. It has the easiest ability to get its molecules up into the gas phase. And of these 4 liquids, water has the strongest intermolecular force strength. And you know that because it has the fewest molecules get into the gas phase, which makes it have the lowest pressure. Let's think about how this happens on the molecular scale. And we're going to do this using things that are like the Boltzmann plots we looked at for gases. So these are number of molecules on the y-axis and how much energy those molecules have on the x-axis. And so we see a trend like we saw for the Boltzmann distributions. Not very many molecules have very little energy. Not very many molecules have lots of energy. But if we look at this curve at 2 different temperatures, what will happen is at lower temperature, here, you have more molecules at lower energy and fewer molecules at higher energy. At higher temperatures, you have more molecules at moderate energy and more molecules at high energy. If this happens to be the amount of energy it needs to separate 2 molecules from each other, let's say you have a water molecule here, it's attracted to a water molecule here, they're kind of held together by some molecular force strength, you want to pull them apart. It takes a certain amount of energy to pull them apart. That energy is related, of course, to the enthalpy of vaporization. Well, that's this on the x-axis. We're saying that's the amount of energy it requires to pull a couple of water molecules apart. At higher temperature, you have more water molecules that have at least that amount of energy. At low temperature, you have fewer molecules that have at least that amount of energy. So at higher temperature, there are more molecules that can break the intermolecular forces, and therefore more molecules in the gas phase. So that's why increasing temperature leads to higher vapor pressure. If you have 2 different liquids, let's say we had water and we had ethanol. Well, let's do methanol because that's what we were just doing, methanol. Methanol has weaker intermolecular forces, so this is methanol's cutoff for being able to break its intermolecular forces. This is water's cutoff for breaking its intermolecular forces. So at the same temperature, the 2 liquids will have the same distribution of energies because kinetic energy is related to temperature, not what the molecules are. But for methanol, a greater fraction of those molecules have at least enough energy to escape because it's easier for them to escape. At the same temperature, water has fewer molecules that can escape because it takes more energy for them to escape because you've been shifted over, the cutoff for breaking the molecules apart has been shifted over to higher energy. So strong intermolecular forces lead to low vapor pressure. So you can look at things, multiple plots of vapor pressure versus temperature, and what you see is that things that have higher vapor pressures at lower temperature have weak IMFs, and things that have lower vapor pressure and take a higher temperature to get to a high temperature, those have stronger IMFs. And in all cases, the intermolecular forces, vapor pressure increases with increasing temperature. Okay, now we're going to talk about boiling point. Boiling point is the temperature, it represents a temperature. It's a temperature at which the vapor pressure reaches the external atmospheric pressure. And that external atmospheric pressure is 1 atmosphere at sea level on an average day. But it can be lots of different things in different places. So when you're at high altitude, it can be down around 95 degrees. If you're in an airplane which has very reduced pressure in your cabin, it can be even lower. So what happens is, to find the boiling point of a liquid at any particular external pressure, you take that pressure, let's say 400 milliliters of mercury, which is actually very low, you draw a line across, and the temperature at which each of these liquids crosses that line is the boiling point at that pressure. So carbon disulfide has a boiling point of about 28 degrees at an external pressure of 400 milliliters of mercury. Methanol has a boiling point of about 47 degrees at that external pressure. If the external pressure was 600 millimeters of mercury, then the boiling point of carbon disulfide wouldn't be 28 degrees. It would be around 39 degrees. And so every liquid has a lot of different boiling points depending on what the external pressure is. So what do we mean by boiling point when we talk about boiling point of something? What we mean is the normal boiling point. And the normal boiling point is the point at which the vapor pressure reaches 760 millimeters, meaning at which the vapor pressure reaches 1 atmosphere. And so what you do is you take the vapor pressure curves and you see where they cross 1 atmosphere. And that gives you the normal boiling point. So the normal boiling point of diethyl ether is around, looks like around 35 degrees. Oh yeah, look, 35 degrees. The normal boiling point of ethanol, where it crosses 1 atmosphere, is 78.3 degrees, and the normal boiling point of water is 100 degrees. And the reason that it happens to be 100 degrees is that happens to be the temperature at which the vapor pressure curve for water crosses 1 atmosphere. Okay. The trends, of course, is that as intermolecular force strength increases, you have to get to a higher temperature to get your vapor pressure up to 1 atmosphere. So normal boiling point increases with increasing intermolecular force strength. Okay, so let's look at our summary. As intermolecular force strength increases, vapor pressure will decrease. As vapor pressure decreases, you have to get to a higher temperature to get the molecules into the gas phase, in which case it takes harder to get the vapor pressure up to 1 atmosphere. So the boiling point increases. And the other thing that's important is the delta H of vaporization. As the intermolecular force strength increases, the molecules stick together better. It takes more energy to remove them from each other, so the enthalpy of vaporization also increases. The vapor pressure curve can be used to predict whether or not condensation will happen, whether something will rain, essentially. And what you do is you take the vapor pressure of a liquid, this happens to be for water, and what you do is you say, what is the vapor pressure, what is the temperature, and see where you are. So let's say we had a vapor pressure of water equal to, I'm going to make up, 200 millimeters of mercury at 25 degrees Celsius. What you do is you go on this plot, you go to 200 millimeters of mercury, 25 millimeter, 25 degrees Celsius, and you figure out where you are. If you're above the vapor pressure curve, that means there's too much water in the gas phase, and so it will condense. And when it condenses, as the water condenses, the vapor pressure will decrease because the water is going from the gas phase into the liquid phase. So the amount of gas decreases because it's becoming a liquid. As the gas decreases, the vapor pressure decreases, as it will decrease until you reach the vapor pressure curve. And this whole idea is where the idea of dew point comes from. It comes from the dew point is at any particular temperature, at any particular vapor pressure for water. It's the temperature at which that would condense at. If, on the other hand, you had, for example, a temperature of 50 degrees Celsius, which is, you don't get that in real life, you get it in labs, and let's say the vapor pressure was equal to 50 millimeters of mercury, then you would be 50 millimeters of mercury at 50 degrees, you'd be right here, in which case you're below the vapor pressure curve, in which case you just have some water vapor in the atmosphere, and there'd be no, and it would not condense. The fraction, the vapor pressure actual, divided by the equilibrium vapor pressure, meaning the vapor pressure from the curve, gives you the percent humidity. So when you have percent humidity in weather reports, it's the fraction of the vapor pressure that's actually in the air compared to the vapor pressure that the water can hold at that particular temperature. Okay. The last thing we'll do in this lecturette is we will look at how we obtain delta H vaporization data from, or delta H vaporization values from experimental data. And the experimental data relies on the conversion of the experimental data to the value relies on what's called the Clausius-Clapeyron equation, which says that the natural log of the vapor pressure, so that P is vapor pressure, is equal to minus the delta H of vaporization divided by the gas constant R times the temperature in Kelvin plus some constant. It turns out that constant doesn't matter for anything. And so what you do basically is you take this vapor pressure curve and you redo it so it fits and makes a line for this, and that's what we're going to look at. So what you do is you take this equation and you essentially write it as a linear equation. So that will be the y values, the natural log of pressure. We'll rearrange this by splitting out the t over to here, so that's 1 over t. And so this now becomes the slope. That becomes the x value. And so what we do is we plot our y values, ln of p, versus our x values, 1 over the temperature. And then the slope, sorry, let me do this here, equals minus the delta H of vaporization divided by R. So let's go ahead and look at that for an example. So these are some experimental information, and you'll be doing this in a lab. And so you'll have your own ones of this to do. And these are our temperatures. These are our vapor pressures. And we're going to make a plot, and we're going to get the slope. And so I have handily added those values into an Excel spreadsheet. So those are our temperatures in Kelvin. They have to be in Kelvin. These are our pressures. It doesn't really matter what unit the pressures are in. And so I need to make the 1 over the temperature values, and I do that by hitting equals 1 divided by, and I click on that cell and hit enter. And then I can drag this little box down, and it will repeat that calculation for all 4 things. And then we also need the natural log of P. And so what I do is I say equals ln, and then a parentheses. Actually, I'm not sure if I need the parentheses, but it works. And that's the natural log of that number. And then I'll drag that down. And I want to make a plot of this on my x-axis, this on my y-axis. So I press the upper level thing there. I hold my control key down, press that. I insert a scatter plot. There it is. I delete these meaningless little labels. Delete. Delete. And then I need to get the slope of the line that goes through these points. And the way you do that is you hover over a point, right-click, Add trend line. Trend line is the line that goes through those points. Leave it at linear, and then say display equation on chart. And so that gives me my y equals mx plus b equation. So my slope is minus 2,993.8. Okay, so the slope of our plot is minus 2,993.8, and the units for those are kelvins. And so what we do is we rearrange this equation here for delta H of vaporization, and delta H of vaporization is going to be equal to minus the slope, so it's minus negative 2,993.8 kelvins times R, 8.314 joules per Kelvin mole. So kelvins cancel, and when we multiply that through, we get 24,900 joules per mole, which we would normally convert to kilojoules per mole, so it's 24.9 kilojoules per mole. And that's how one finds delta H using the plotting method of the Clausius-Clapeyron equation. The Clausius-Clapeyron equation also has a two-point version, and this is mainly used if you know some data and you want to find out one other. So this has five variables: P1, P2, T1, T2, and delta H of vaporization. And so this version of the equation is used if you know four. If you know four of these, and you want to find the fifth of them, the last of them. So let's look at an example of this. The vapor pressure of aluminum is 400 millimeters of mercury at high temperature, because it's a metal. It's at 2,590 Kelvin. If we say that the delta H of vaporization, the enthalpy of vaporization, is 296 kilojoules per mole, and it doesn't change as temperature changes, we want to calculate the vapor pressure of aluminum at a different temperature, 2,560 Kelvin. So we know P1, that's 400 millimeters of mercury. We know that we're looking for P2. We're asking for what is, calculate the vapor pressure. So we're looking for P2. T1 is 2,590 Kelvin. T2 is 2,560 Kelvin. And delta H of vaporization is, I'm going to change that to joules per mole, 296,000 joules per mole. Okay, so what we do then is we basically plug in everything and we solve for P2. So from here on it's just algebra. So the ln of P2 over 400 millimeters of mercury is equal to minus 296,000 joules per mole over 8.314 joules per Kelvin mole times 1 over T2, so that's 2,560 Kelvin, minus 1 over T1, 2,590 Kelvin. All right, so I generally do this in pieces. I'm going to do this part first. And if you have a 1 over x key on your calculator, that helps a lot. And so you can put in 2560, hit your 1 over x key, minus 2590, hit your 1 over x key, and that comes out to be 4.525 times 10 to the minus 10 to the minus 6. And the units for that are 1 over Kelvin. So I'm just going to put that over Kelvin. So that's what that part is. This part here is 296,000 divided by 8.314. So that comes out to be 35600. And our units for that are joules cancel, moles cancel. So that's also just over Kelvin. No, it's not. It's just kelvins are on top, because Kelvin's on the bottom. And so that's a negative there. And so that means that that side of the equation comes out to be minus 0.1611 when you multiply through. Now, that equals the ln of P2 over 400 millimeters of mercury. A piece of log math you may or may not know is that the natural log, or any log, of like A over B, for example, means that is equal to the natural log of A minus the natural log of B. So the ln of P2 is equal to, oh no, sorry, I can change this part, the ln of P2 minus the ln of 400 millimeters of mercury equals minus 0.1611. And so you can take the ln of 400, that's just a number then, get you closer to your answer. So that comes out to be the ln of P2 minus 5.99 equals negative 0.1611. And from that, you have P2, or the ln of P2, is equal to 5.830. Finally, running out of room here, so I'm going to put this over here. Finally, the way you get rid of the log is you take both sides, you raise both sides from e to the x. So another piece of log math is e to the ln of a equals a. So if we take e to the ln of P2, that gives you P2, and then that equals e to the 5.830. And so when you do that on your calculator, which is the inverse log function, it's not your EE key as in your exponent key. So 5.830 EX, so it comes out to 340 millimeters of mercury. And that's your final answer. And that makes sense that it's lower than our initial answer because the temperature is lower. So the temperature decreased. So the vapor pressure ought to have decreased from 400, and in fact it did. So that's the use of the two-point equation. It's all basically setting up for about 25 seconds and then doing a few minutes of algebra. Again, make sure, of course, that your temperatures are in Kelvin. Because your pressures are divided by each other, you don't have to convert those into any other units, but the units you come up with in your answer will be the same as you started with. Finally, we're going to look at a couple of special other properties of liquids. First is surface tension, and the idea of surface tension you've seen. If you take some water and you put something on it that ought to sink, sometimes if it's not very heavy, it won't sink. So you can take, if you're careful, you can take a paper clip and lie it on top of on the surface of a water, and you've seen bugs on tops of water without sinking in. And the reason that this happens is the intermolecular forces between molecules inside the liquid are greater than those on the surface of the liquid. So inside the liquid, a water molecule, each of these represents a water molecule, has intermolecular forces to a whole bunch of water molecules around it. Those on the surface only have interactions with those below it and to its side. So they have about half as much. The ones on the surface have about half as much interaction as the ones inside. Therefore, inside molecules are more stable. And therefore, liquids want to have more molecules inside and less molecules on the surface. So they minimize the surface. It turns out that the best shape for minimizing surface area is a sphere. That is, a sphere has the most molecules inside and the fewest molecules on the surface. So what happens is if you take a paperclip or a bug foot, here's a bug foot, and the bug foot's trying to press down to the water resists letting it go in there because that would increase the surface area. So that's called surface tension. You can see surface tension, you can measure it by looking at what's called a contact angle. And a contact angle is basically how big a droplet stands up against the force of gravity. So the force of gravity is if you have some liquid, the force of gravity is trying to take the liquid and smear it out really, really low. Surface tension is trying to make it a sphere, because sphere is the best thing. And so a drop is really, the shape of a drop is really a contest between gravity pushing down, trying to make it not a drop, not a sphere, surface tension pushing up essentially, or trying to just make it a sphere. So the more spherical something is, the greater its surface tension. And also, if it's on a surface, it also has to do with the attraction of those liquid molecules to the surface, which you try to minimize when you're measuring this. So what happens is you can measure that with a contact angle. You basically take the edge of the droplet and measure how much is coming off, and that's called the contact angle. And the larger the contact angle, that means the droplet's doing a better job of fighting against gravity, which means its surface tension is greater. And you can look at surface tension and try to make kind of generalizations about surface tension versus intermolecular forces. And what you find when you do that is that most times things with stronger intermolecular forces have stronger surface tensions, but that's not always true. So, for example, mercury has a very high boiling point, which means it has very high intermolecular forces, and it's got a very high surface tension. Water, likewise, has a relatively high boiling point. It has a high surface tension. But if you look at, for example, octane's boiling point is higher than water's, so it has stronger intermolecular forces, but its surface tension is significantly lower. So there's kind of a trend, but you can't count on it. So very often things with strong intermolecular forces will have stronger surface tension, but not always. Okay, next thing is viscosity. Viscosity is essentially resistance to flow. So it's essentially how quickly a liquid will move. It's how thick it is. And that actually does not have good intermolecular force correlations. What it really correlates to is more than not the length of the molecules. So longer molecules have a high viscosity. And there's no really good correlation with IMF strength. And so what happens is mercury, which has very strong intermolecular forces, has very low viscosity. It flows really easily. Things like cornstarch, when you put cornstarch in water, cornstarch is made of big, long molecules. And what happens is things that have big, long molecules, if they try to flow, they get in each other's way. And it's kind of like trying to have a bunch of spaghetti flow. Even though the molecules might not be sticking to each other very much, they just get entangled just because they're long and they get entangled. So things that have long molecules tend to have high viscosity. Things that have shorter, more spherical, small molecules tend to have low viscosity. The last special thing we'll talk about, which is actually not really a property of the liquid alone, is capillary action. And the idea is that when you have a liquid in contact with a surface, that liquid might be attracted, the molecules liquid might be more attracted to the surface than to the other liquid molecules. And so if you take water, this here is water, and that's glass. What happens is the water is more attracted to the surface of the glass than it is to the other water molecules. And because of that, the water, if you have a tube, the water will draw up inside the tube. And that's called capillary action. And it has to do with increased intermolecular forces between the water and the glass compared to just the water. If you take glass and mercury, this stuff here is mercury. Mercury is more attracted to itself than the glass. And so when you plunge the very same glass tube into the mercury, it does not drop it. So there's no capillary action between mercury and the glass, but there is between water and the glass. Those forces between, those kind of intermolecular forces between two different species is called an adhesive force. Those between the same species, like water and water, is a cohesive force.